So the second part actually is a so-called client puzzle. So this actually is also a useful tool that can be used to prevent denial of service. And this tool is based on the concept of proof of work. So capture is based on the different capabilities of human and machine. That means you send a capture challenge, then only human can solve the challenge, but the machine actually cannot solve the challenge. And the client puzzle actually is another technique. So it's called a proof of work. So if you are a real initiator of a request, so basically the server will send you some client puzzle. You need to solve the client puzzle in order to get the service or to get the connection. Right? So this to solve this client puzzle, you need to do a little amount of work. So that's why we call it proof of work. You need to prove to the server you have done a little amount of work to solve this client puzzle. So if you prove, okay, you have done the work, then you will be allowed to access the service. Otherwise, the server will reject your connection. So why this can be used to prevent denial of service attack? Because, so first of all, if you use reflectors or even zombie machines, so similar as a capture scenario. So when the server sends some challenge, here the challenge is a client puzzle, those machines will not try to solve the client puzzle, because these machines actually, they do not intend to connect to the server, so they will not try to solve those client puzzles. And another advantage of using client puzzle is if you want to have a lot of connections established, then you need to solve a lot of client puzzles, right? So it's similar as the slow process of authentication. If we give only a little amount of work for each connection, then the normal user will not be affected. However, if the attacker want to generate a lot of connections, then the accumulated amount of work will become huge. So in this case, the attacker may not be able to cannot solve all the client puzzles within a short time, because if we accumulate different client puzzles for different connections, the total amount of work can be huge. So this is how we can use the client puzzle to prevent the denial of service attack. And the details actually you can find in this paper, but this paper is quite technical paper. So they introduce this idea, but actually they are not the first one introducing the idea, but they formalize this idea and then they present some formal analysis and so on. So there are a lot of mathematics involved in the paper, but you don't need to really worry about the details of those mathematics. So later we will see some examples, then you can understand. So, for example, how to create a puzzle, how to measure the strength or the security level of a client puzzle. Right, so this is basically how we use client puzzle. As I mentioned, in this case, we need the client to solve some problem. So to prove that the client has done some work in order to to have the connection established with the server. Right, so the client puzzle, usually will be used based on some cryptographic problem. That means some problem that cannot be easily solved. So usually in cryptography, we have problems that cannot be easily solved. And one typical tool that can be used in this scenario is the same tool you studied before, the hash function. Right? So because we know hash function is one way, right? So hash function is one way. That means if you give a hash value, actually you cannot find out the pre-image. So what you can do is to do a brute force, right? So then, to give you a very simple example, suppose I create an input, a secret input, and then I hash this input to get a hash output. If I give you the entire hash output, of course you cannot find the input because it's because this is a one-way function. And if you want to do the brute force, it may take a lot of time. That means you need to do a lot of work. But what happens if I give you, say, we have k-bit input. I give you k minus 1 bit. I only hide the first bit. Then what you can do is just to try the two possibilities of the first bit. That means you at most try twice, you can find the solution, right? So to make the puzzle a little more difficult, maybe I don't hide 1 bit, I had 2 bit or 3 bits. So in this case, I give you the remaining input. You just try to find the missing part. So the missing part can be like 1 bit, 2 bit, or n bit. So in this case, the security level or the difficulty of solving the puzzle now depends on how many missing bits you have, right? So that's basically the idea, right? So we can use some crypto algorithm like the hash function to design such a client puzzle, right? So in this case, we need to make sure the work required to like generate the puzzle or verify the solution of the puzzle should be very quick, because if say the generation of the puzzle is very expensive, then this becomes another point for intrusion detect for denial service attack, right? So you implement a client puzzle to prevent denial service attack. But if the generation of the client puzzle require a lot of resource, then of course this is not this is a useless tool, because the client puzzle itself becomes a point for denial service attack. So we need to make sure the generation and the verification of the solution for the client puzzle must be very quick, very efficient, right? And for the normal user, you should not require the user to perform a lot of work, just a small amount of work. But for the attacker, if the attacker wants to have a lot of requests, then the attacker need to do a huge amount of work. So that's the requirement for designing a client puzzle. Right, so this is a picture illustrates the scenario of this client puzzle protocol. So the client will send a request, then maybe the server will check. For example, in the TCP sync flooding, the server will check the buffer. So if the buffer is empty, then you don't need to do any you don't need to enable the client puzzle. So you just establish the connection. However, if the server now discover that okay, the buffer is very full, is almost full, like maybe say 80% full. So in this case, the server may suspect there is a denial service attack. Then the server can enable this client puzzle protocol to send the client puzzle to the client. Client basically will need to perform a little amount of work to prove, okay, this is a real client. Then the server will verify this solution, and then if the solution is valid, then basically the server will allow the client to establish the connection. Right, so that's the process of using this client puzzle protocol. Okay, so basically in order to implement this kind of client puzzle protocol, so we may need to have some special software installed on the client side, because the software will need to recognize a puzzle and then generate a solution. So, but this will not be a big problem, because you can, for example, for the browser, you can just add a plugin. You can just design implement a plugin which can implement this client puzzle protocol. Okay, so in the previous case, we just look at the simplest scenario. So we only use one single puzzle to challenge the client. So the client basically will need to use to solve this client puzzle in order to get the access, get the connection. However, in general, actually, we can, instead of using one very big client puzzle, we can use a set of small client puzzles. And later you will see actually the second approach is better. That means instead of sending a large client puzzle to the user, we prepare a set of small client puzzles. And then the client will need to solve all these client puzzles one by one. And overall, so if you look at the overall complexity, maybe they are the same. For example, you can have 10 bits missing, or you can have 5 client puzzles, each with maybe 2 bits missing, right? So you may think, okay, overall complexity is the same, but actually, when later we will see, when you do the analysis, you will find if we use a set of small client puzzles, then the security is better, right? So we will look at the reason later when we look at how a set of small puzzle can actually enhance the security. So this is how we generate one puzzle. So it can be a large client puzzle or just one of the sub puzzles, right? So if you only have one large puzzle, then client puzzle, then this is the whole client puzzle need to be solved. If you have a set of small sub puzzles, then this is one of them. All right. So the idea is the same as I just mentioned. So basically, the server will try to create some hash value, and now the server will ask the client to find some missing bits in the pre-image, right? So, but how to generate this pre-image, right? So actually, the server can generate this pre-image by using some secret and some data associated with the connection. For example, the user want to connect to a particular service, you can put some data like a timestamp, like when this request is sent, and then what's the service to be accessed, and so on. You can put them in this input, and then the server maintain also a secret. So now the server hash this input to generate the second part. This is X. So X actually is the pre-image that will be used to generate the final client puzzle, which is Y. So we hash twice here. However, so because hash is very quick, so you can do hash very efficiently. So the generation of the client puzzle actually is very quick. So the server just use some secret, like this is like maybe a secret key, like a 128-bit secret key, and then some other data associated with the connection. You hash this input to generate X, and then you hash this X again, you get Y. So J here means this is a J's subpuzzle. But if you only have one client puzzle, then you can ignore the J here. So J is to indicate if you have a set of subpuzzle, then this J is the J's subpuzzle. So in this case, actually, basically what you will give to the client is this Y together with part of the pre-image. So the remaining like L minus K bits of the pre-image, but you have K bits hidden from the client. For here, K can be 1, can be 2, can be 3. So if you have, say, 3, K equal to 3, that means you take away the 3 bits from the X, and then you give the remaining L minus 3 bits, and together with this Y to the client. The client now will need to find the 3 missing bits, or K missing bits here. So, however, because the hash is one way, so you cannot directly find X from Y. And also, the S is a secret only known by the server. So the client cannot do the calculate S in this direction. So the only way the client can solve the puzzle is to do a brute force. You try to enumerate all the possible missing K bits, right? So in this case, if you can produce the entire pre-image of Y, that means that you perform this brute force search, right? So the only way to solve this client puzzle to find the K missing bit is to do a brute force search. That means you try all the possible K bit string to find which one combined with this remaining part can produce the correct pre-image of Y. So that's what you need to, basically the client need to solve for this particular subpuzzle, right? So for the J subpuzzle, you can take away K bits, and then to solve this one, the client need to find this K missing bits, right? So this is the idea of generating a client puzzle using hash function. So server can do this process very quickly because server do the hash from the secret and the server secret and also some other data. So the server only need 2 hashes to generate the puzzle. To verify the puzzle is also very quick because actually you can also verify the puzzle. Once you give the solution, the server can do the verification of the puzzle very quickly. However, to find the solution, because hash is one way and the S is unknown to the client, to find the solution is not that efficient, depending on the size of the K. So if K is small, actually it's efficient, but if K is not that small, then the client need a certain amount of computation to find the solution. So in general, how difficult the climb puzzle is? So the difficulty is depending on the value of k. If you have only one bit missing, that means you give the remaining L minus 1 bit plus the Y, but you only have one bit missing, then in the worst case, you only need to try twice, right? Because if one bit is missing, you only need to brute force two possibilities, either 0 or 1. But if you have 2 bits missing, the worst case, you need to try 4 times, because 2 bits, that's 2 to the power of 2, right? If you have 3 bits missing, you need to try 2 to the power 3 times in the worst case. So in general, you need to, in the worst case, if you want to solve a climb puzzle, you need to try 2 to the power k. That means all the possible combinations of k-bit string. So that's the worst case. But on average, you only need 2 to the power k minus 1. So this is the average or the expected number of hash required, right? So this is roughly 2 to the power of k minus 1. Right, so why this is roughly? Because there is some small tail removed here, okay? So if you remember how to calculate the expected value. So actually you can easily calculate why this is 2 to the power of k minus 1. So, right, so you say if you have like a k bit missing, right? So if you have k bits missing, so basically if you are lucky, so you may try once, you get the solution, right? Because there are k bit string missing, you need to find this k bit string. So if you try one hash, you randomly try one k bit string, maybe you are lucky. In this case, you already found a solution. Then you only need one hash, right? So if you are less lucky, maybe you need to try twice. You may need to try 3 times, and the worst case, you may need to try 2 to the power k so many times, right? So if you are not lucky, then the worst case, you need to try all the combinations, right? So all these are possible, right? So suppose 2 to the power k equal to n, right? Actually, so if you want to calculate the expected value, right? So suppose you want to calculate expected number of hash, then this is the sum of I, and then the probability, the number of hash equal to I, right? So this is how to calculate the expected value. I is from 1 to n. Right, so if you calculate this one, this becomes, so all these cases will have the equal probability. So in this case, basically you have 1 times n, 1 times 1 over n plus 2 times 1 over n. Because the probability of all these situations, the probability is the same for all these cases. So if you do the calculation, eventually you have n times 1 over n. So you have 1 plus 2 plus n, 1 times m. So you have n times n plus 1 divided by 2 times 1 over n, right? So then you have n divided 2 plus 1 over 2, right? So the tail here is 1 over 2. So roughly this is n over 2. So 2 to the power k minus 1 plus 1 over 2. Right, so because we assume n is 2 to the power k. So roughly, the expected value will be 2 to the power of k minus 1. So we just ignore this tail, okay? So that's why the expected number actually is roughly half of the worst case. So if all these events have the same probability, then the average case is the expected number is only like half of the worst case, right? So this is how we derive this expected number of hash for solving a climb puzzle. All right, so this is just for one climb puzzle. But if you have multiple climb puzzle, then we will need to look at the distribution, right? So if you have m multiple climb puzzle, then the overall difficulty actually will be m times 2 to the power of k minus 1, because each puzzle you will need to use 2 2 to the power of k minus 1 hashes to find the solution. So if you have m subpuzzles, you need to have m times 2 to the power of k minus 1. And the worst case is m times 2 to the power of k. Okay, so that's what you need to perform if you want to solve all the n subpuzzles. Right, so if you have one big subpuzzle, the difficulty actually can be same as a small set of small subpuzzles. Right? However, the distributions are quite different. So if you look at the distributions, actually they are different, although the complexity, the overall complexity look similar, right? So if say we have one single puzzle, big puzzle, client puzzle, m equal to 1, we only have one single puzzle, but say k equal to 4, then the expected number of hash is roughly 4 times 2 to the power of k minus 1, which will give you 8. Oh, sorry, 1 times 2 to the power of 4 minus 1, which will give you 8. On the other hand, so if say we have 4 subpuzzles, each subpuzzle with a smaller k equal to 2, we will again have the same number of expected number of hashes for the 4 subpuzzles. That means you again will have this 8 expected number of hash for solving 4 relatively smaller subpuzzles. So it looks the difficulty. So the difficulty for the client actually is the same. So the expected number of hash the client need to perform should be the same. So it looks the security will be the same, right? So because to solve both cases, either a big client puzzle or a set of small client puzzles, the number of hash required is the same. So in this case, you may think the security is the same, but actually the security is different. The second one is better than the first one. Why the second one is better than the first one? Because the distributions are different. Okay, so if we have the first case, actually k equal to 4, we have a single puzzle, then you have a uniform distribution. Because you may need 1 hash. If you are lucky, you need 1 hash. If you are less lucky, you need 16 hashes. So, however, all of them have the same probability. So in this case, you have a so-called uniform distribution. But if you have 4 or like a set of subpuzzles, and each actually has a smaller k, so overall expected hash, they are similar. So here, I highlight the difference. Actually, the overall is the expected number of hash is still different. Here we need 10, here we need 8.5. So why 8.5? Because this is 2 to the power of k minus 1 plus 1 over 2. So here we count the 1 over 2 here. So this is 8.5. Here each subpuzzle will have 2 to the power of 1 plus 1 over 2, which is 2.5, but you have 4. So you multiply 4, you have 10. So you may say, okay, this one is secure because this one is larger, this number is larger. But this is not the real reason why this second one is more secure. The reason the second one is more secure is because now the second one has this distribution, a normal distribution, or we call it Gaussian distribution. The first one has a uniform distribution. Okay, so why this one is more secure? So first, why we will have a distribution like this? Alright, so if you have 4 subpuzzles, then you need to perform in minimum 4 hashes, right? So that's what you need to perform at least, because you have 4 subpuzzles, so you need to do 4 hashes, right? So if you have 4 subpuzzles, then the minimum number of hash you need to perform is 4. Why? Because you need at least 1 hash for the first puzzle, so you have 4 subpuzzles here, right? So you need to perform at least 1 hash to solve the first subpuzzle, 1 hash to solve the. So in this case, you need at least 4 hashes, right? So you cannot use 1 hash or 3 hash to solve all the 4 subpuzzles. Then the second case, if you are less lucky, you may need to perform 2 hashes for one of the subpuzzles, right? So in this case, so maybe one of them you will need to perform 2 hashes. If one of them requires 2 hashes, then you will need to have total 5 hashes. So now basically total you need to have 5 hashes. But there are different situations. You may need 1 hash here, 1 hash here, 1 hash here, 2 hash here. You may need 1 hash here, 1 here, 2 here, 1 here. It's also 5 hashes. You may need 1, 2, 1, 1, also 5 hashes. 2, 1, 1, 1, also 5 hashes. So if you perform 5 hashes, actually you have 4 possible cases, right? So that's why if you look at here, so 4 hash you need only have 1 case, but 5 hash actually you have 4 cases. And then how about you perform 6 hashes? You will have even more cases, right? Even more possible cases for 6 hashes. So basically the number of cases will increase, and the maximum number of possibility will appear when you have the expected value, which is 10. If you have expected value, the number of possible cases is the maximum. Then it will drop. So the last case, the last one is you need 16 hashes. Because the worst case, you try 4 hash for the first one. That means you try all the possibility for the first subpuzzle. You try all the 4 possibility for the second one. You try all the possibility for the third one and the last one. That means you are not lucky for each subpuzzle. Every one you try all the possibilities. In this case, you need 16 hashes. And the 16 hash also only have 1 case, because you try the worst number of hashes for each case, for each subpuzzle. So now you have a distribution like this, right? So the distribution becomes like this, basically. Now this is why we have such a distribution, right? So this explains the reason. And then the next question is, why this one is more secure? Why this one is more secure, right? So if I give you a simple example. Suppose, say I try 3 hashes, I try 5 hashes. For the first case, what's the probability that you will be successful? The probability will be, you have 5 hashes here, right? So the probability will be the area of this area divided by the whole area, right? So that's the probability, basically, right? So because you have 5, and you overall you have 1 to 16, so you have 16 values. So basically, if you try 5 times, the probability the attacker can break the puzzle is 5 over 16. But if you only try 5 hashes here, what's the probability the attacker will be successful? It's the area here divided by the whole area here. So it's much smaller. So in general, if you try a small number of hashes for the first case, the chance that you can pass is high. But for the second case, if you try a small number of hashes, the chance you can the chance you can pass the verification is very low. So in this case, actually the second one is much better, because this one actually has a smaller standard deviation compared with the first one. Because this one, the majority of the cases are near the expected value. That means with very high probability, you need to perform expected number of hashes to pass the verification. This one is very unstable. Even if you perform a small number of hashes, you can have a high probability to pass the verification. So that's why we use the second one. If we use second one, the security will be better than the first one, right? So that's the reason. That explains the reason why we have. If we use the second approach, the security will be better. Okay, so then this basically this is the same picture. I just explained the meaning. So what is y, what is x, right? And then if you look at the distribution, basically for the first one, so you have one case for each possibility, right? So for each number of hash, you have one possible case. And then for the second one, actually you can have different distribution. For 4 hash, you only have 1 case. 5 hash, you have 4 cases. 6 hash, you have 10 cases, and so on. Right, so the distribution becomes like a normal distribution, right? Okay, so this is basically the difference. And then in assignment 2, you need to do an exercise. So in assignment 2, you need to do exercise. So the exercise is similar to the example given in the lecture notes. Of course, the numbers are now different. Right, so basically these two cases, they will have the same number of expected hash. Roughly they will have the same number of expected hash. However, again, now because one is a single puzzle, one is a set of subpuzzle, the distribution will look different. So now what you need to do is to find the distribution for the number of cases required for each puzzle. So for the first one, it's very simple. The first one is very simple, okay? You have a uniform distribution. The second one, it will have a normal distribution, right? So the second one, because we have 8 subpuzzles, each subpuzzle has a k equal to 3. And there are different ways to solve the problem. So one way is you can simply write a program, right? You can write a program. So for the first one, actually you don't even need to write a program. But for the second one, to find the distribution like this, you need to write a program, right? So you can think. About this question, how to basically enumerate like the distribution, like for each possible number of hash, how to find out what is the number of possible cases, right? So you can simply write a program to solve this problem if you want. Okay, so then you need to also draw a graph to show the distribution, and then you show the average number of hashes and the standard deviation required for each puzzle. Right, so that's what you need to do. Basically, you can see if we have 8 subpuzzles, so k equal to 3, that means each subpuzzle you need to have the possible number of hash is from 1 to 8. 2 to the power 3 is 8, right? So you can basically try to enumerate. Say you have 8 subpuzzles, each one will have 1 to 8 possible hashes. Then you can try to write. You can simply write like a C or C++ or Java program to see if you sum up all the possible number of hash, then what will be the distribution? What will the distribution look like? So you can simply write a program to do that. Okay, so this is what you need to do in assignment 2. Right, so the distribution is basically, so if you calculate standard deviation, right, so maybe the last remark before we take a break. So someone tried to do the calculate standard deviation using this set of number. So but if you use this set of number to calculate standard deviation, it's different. So it's different from the number given here. So if you use the numbers given in the table to calculate the standard deviation, you'll find it's different from here. So the reason is when you calculate standard deviation, you should not use this row, right? What you need to use is this column. This is the distribution. You need to calculate the mean and the standard deviation for this column, right? So you have 1, 4, 5, 5, like 10, 6, and so on. So this is basically the column you calculate standard deviation. It's not this part. So if you use this row to calculate standard deviation, then you find actually the answer is different from the standard deviation given in the lecture notes. Okay, so that's how the client puzzle can be used, can be designed. Instead of using a single client puzzle, we can use a set of small client puzzles in order to increase the security of the system. Okay, so we look at how the client puzzle actually can be generated, and then also how to improve the security by using a set of sub-puzzles instead of one single puzzle. And then we will look at how, basically, how we implement this kind of puzzle in the system. So in general, we don't need to always enable the client puzzle in the system. So we can enable the client puzzle only when we have some sort of like attack. So the server may suspect there is a denial service attack, then the server can enable the puzzle, and then you can just let each client to pass the verification. Let each client pass the verification before you run the service. Right. So if say in the TCP sync flooding, if the buffer is still empty, quite empty, then you don't need to run the client puzzle. Right. So then actually some students just ask, what's the content used by the server? So in the previous slide, it says the server need to use a secret. Right. This is like a secret key, say like a long secret string. So you should use a large secret number instead of a short secret. And then some other content actually included in the calculation of this X, which is a preimage of the puzzle, is basically the other content included in the calculation of this preimage of the client puzzle actually includes the timestamp. So timestamp is for example, the time when this connection is received, and then the service you want to access. For example, what is the protocol you want to connect, where the connection comes from, what is the protocol you want to execute. And then J is again here the index of the subpuzzle. So if you only have one subpuzzle, then actually you don't need to include this J. But if you have, say, a set of small subpuzzles, then you need to tell which subpuzzle actually is generated based on the index J. So this will form the input for the server to create the client puzzle. So in this case, basically the client will send a request, and let's say the server now identified there is a potential denial service attack. Then the server basically will generate a client puzzle based on this based on its secret and also the timestamp, like the service the client want to access, and the index of the puzzle. Then you can generate basically the X and Y, and then you take away part of the X, you give the remaining of the X and also the Y to the client. So the client will need to find the missing bits in the X in order to pass the verification. So the server basically can verify whether the solution, the missing bits provided by the client is correct or not. If it is correct, then you grant the access. You continue the service. Okay, so right, so maybe I don't show the answer yet. So what information should be stored? So we said before, so in order to make sure this client puzzle will not become the target of a denial service attack, we need to ensure the server does not need to do a lot of computation, because otherwise the server will, so this client puzzle itself becomes a target for denial service attack. Then the second question is, besides the computation, does the server need to store anything? Because the problem of this buffer overflow in the, sorry, not buffer overflow, this TCP sync flooding attack is the buffer actually is limited. So if you have a lot of half-open connections, then the buffer is full. So similar problem can happen here. When you create, when someone initiates a request, you generate a puzzle. If you need to store something for this puzzle, for example, if you want to verify the puzzle, the solution later, you need to store some information. Then in this case, actually this again becomes a problem, because you will still need a new buffer to store the information, for each client puzzle, right? So if you need to have such kind of buffer to be used for the client puzzle protocol, then this buffer can again become the target of denial service attack. All right. So the good thing here is if you look at the design of the client puzzle, then the server actually does not need to store anything, because if you look at how this client puzzle is generated, so we can, if the server keeps S, the server actually keeps this secret S, and the server generate X and then generate Y. based on the input here. So the S timestamp, the service request, and the index. And if, say, we require the client to support the missing K bit, to provide the, supply the missing K bit in the X, and then also the service to be to access, and also the timestamp, then actually the server can recompute everything from the response and from the client, and also the server secret. So essentially the server only need to keep the secret. So if the server keeps the secret S, then the verification can be done based on the secret S and also the solution provided by the client. So in this case, actually the server does not need to store anything. So essentially, we don't need to have a buffer to be kept by the server for verifying the client puzzle, and we only require very little computation. Essentially, the two hash evaluation in order to generate and verify the puzzle. So in this case, the client puzzle actually does not require much resource on the server side. So compared with TCP protocol, actually we require much less resource in order to run this client puzzle, right? So this actually is the advantage. Okay, so of course, although I said we only require very little computation, but we still need some computation. Not the computation, total amount of computation is not like nothing. It's not like a zero, so we still need some computation. So in this case, if we say the server actually indeed receive a huge amount of requests for the client puzzle, so there may still be a potential issue with the denial service attack. But in general, so if we say we can only handle, say, 1,000 TCP connection, but if we use client puzzle, maybe we can handle like 10,000 client puzzle connections. So the chance that the attacker can overwhelm the server is smaller, because we require less resource in order to do the generation and also verification of the client puzzle. So this is the client puzzle given in the paper I mentioned at the beginning. And there is another type of client puzzle which is actually the similar. So this client puzzle uses the same proof of work in like Bitcoin. Bitcoin actually uses the same proof of work in used in this client puzzle. So this client puzzle, similar to the previous case, we still use hash function. However, so now the problem to be solved is different. So the problem now is to find a particular value, a particular input of the hash, which will give a special format, like output, or the hash output. So we require the client to generate a special output, a special format hash output by finding some particular input, right? So this is the overall idea about this second client puzzle. So H is a hash function, C is client ID, so NS is a server nonce. Nonce means you can just treat it as a large random number. So this nonce means a number used only once. So you can just simply treat this nonce as a large random number. So we have a nonce from server, nonce from client, timestamp, similar as in the previous case. And the K again is the difficulty level, how difficult to solve the puzzle. And then Y is the rest of the hash value, and S is the resource to be provided. So how does this client puzzle work? Essentially, so now, as I said, the client need to find an X based on the client ID, the server nonce, client nonce. The client need to find an X which will produce a special format hash output. So the special format here is you need to have K0 in the beginning of the output. So if you give an X which does not produce K0 bit in front, then this will not be accepted. So in this case, what the server need to verify is server basically will just use the X provided by the client, and the server hash it. If the hash output has this special format, then the server will accept X. All right. So in this case, the difficulty is to find an X which produce many 0 bits in front of the hash output. Right, so why this is also a difficult problem? Because the hash function, in general, we can treat it as a random function. Like you can consider hash function as some sort of like a near random function, pseudo random function. So in this case, say if you give a X, if you give a random X, the probability 1 bit is equal to 0 is only 50%, 1 over 2, right? So say if you want to have k equal to 1, that means we want to have a hash value which have 1 bit, the first bit equal to 0. So in this case, if you give a random X, the chance that the first bit is 0 is only 1 over 2. That means on average, again, you need to try 2 different X in order to get a 0 bit. So if you have k bits, and again, the expected number of X you need to try will be 2 to the power of k. That means again, if you have k 0 bits, you need to try 2 to the power of k, so many different X in order to, on average, so the expected number of hash you need to try will be 2 to the power of k again. So you need to try so many X in order to generate an output which has a k 0 bit in front, right? So this is the difficulty here is basically based on the fact that the hash function behaves like a random function. If you give an input, a particular bit in the output is 0, is only 50%. That means if you want to have 1 bit equal to 0, so on average you need to try twice to have 1 bit 0. But if you have k bit 0, k 0 bit, then you need to try 2 to the power k so many times. And this is how the basically also the proof of work used in blockchain. So the miners, basically what does the miner do in blockchain, in Bitcoin? So miner is to find the X which produce such a hash output. So if you can find the X which satisfies such an output, the format of the output, then basically you will get the reward. You will get, nowadays you will get 12.5 Bitcoins, right? So the Bitcoin structure actually is following the so-called hash chain, right? So I can give you some rough idea. Okay, so basically now you have a block, right? So you have a block. So inside block, actually you have the hash. This is the hash from the previous block. So basically you have a block. This is the hash value of the previous block. So that's why we have the so-called hash chain. So now basically this is hash, and then you have the transaction. So the transaction actually is stored in a so-called Merkle hash tree, right? So you have a tree here, right? So you have like transactions like this, right? So this is like a transaction 1, transaction 2, and so on. All right, so this is basically the Merkle hash tree store all the transactions. This is the hash from the previous block. Now you need to find the X. So this X can be changed. So the miner will try to do the mining. Basically, the miner will try to find different X here. Right, sorry. So miner will need to try to find different X here so that the hash of this block satisfies the requirement. Say you have many 0 bits in front. If you can find an X which produce a hash, so you hash this block again, this will be given to the next block, right? So if you can find an X which produce a hash of the block satisfying the condition, say you have many 0 bit in front, then you successfully you can successfully put this block in the chain. So only when you can find an X which produce a hash satisfying the requirement, you can put this block in the chain. If you find X which does not satisfy the requirement, then this block will not be recognized by other miners. So only when you can find an X which produce a special format hash output. Basically the output contains many zeros in front, then this block is considered as a valid block. Now this block will be put in the chain, and then the miner will get the reward. So essentially what the miner need to do is to find X for this block, so that when you hash this block, the output satisfies the requirement, then you will get the reward. Right? So nowadays, actually, the mining is not that simple, not that easy. So in the beginning, when blockchain or when Bitcoin was proposed, actually this mining can be done using a normal computer. And nowadays, even if you use GPU, it may not be sufficient to find this solution, because nowadays actually the K becomes larger and larger. So if you have a larger K, that means you need to try more X in order to find a valid like X which produce K 0 bits in front. So the hash used in Bitcoin is the SHA-256. So that's like the SHA-2. You can just say SHA-2, right? Because SHA-1 is nowadays no longer considered secure. So SHA-2 is used in Bitcoin. So here actually we have like a hash chain, because this is the hash of the previous block, and then the hash of this block will be put into the next block, right? So you have a chain of blocks. So if you modify any transaction here, so why the integrity can be preserved? Because if you modify any transaction here, this chain will be broken. Because if you change something here, the hash of this block will no longer be equal to the hash put here. So the chain broke. So that's why people can easily verify. If the chain breaks, that means something has been modified. So if the chain is correct, that means nothing is modified. Okay, so that's how the blockchain works. And the proof of work is essentially the same as in this client puzzle protocol. So basically, you need to find X which produce a special output which contains 0 bits in front. Okay, so that's another client puzzle, and the expected number of hash actually will be the same as the previous one. So this is the process. So the server and the client will generate the nonces, and then the client will need to find this X. So the client again will need to do a brute force. You try different X until you find X which has produce output with many 0 bits in front. So that's what you need to. That's the work you need to complete in order to prove that you have solved the client puzzle. All right. So if you need to try say 2 to the power kx. That means you need to try 2 to the power k hash, because you need to hash the x to check whether the result is correct or not. Right, so basically this is the second client puzzle we can use and to implement the proof of work. Okay, so there are many other versions of the client puzzle proposed. So you can find also some examples in the reading material. So if you are interested, you can find more details. Right, so and then in the client puzzle we looked at in the first part of the lecture. So we actually can solve the client puzzles, subpuzzles in parallel. That means similar as in blockchain, actually you can do the search in parallel. So to make the puzzle even more difficult, actually you can try to make this kind of client puzzle related. That means one subpuzzle need to be first solved in order to solve the second subpuzzle. So in this case, you can actually prevent the user to do the parallel computation to solve the multiple subpuzzles simultaneously. So in this case, you may make the client puzzle even more difficult. So this is another possible way to improve to increase the difficulty of solving the client puzzle.